since this is a continuation of our previous video. Understanding water pressure, Part 1. We will move on directly to the current video. Understanding water pressure, Part 2. In this video we will expand the concepts discussed previously. We will present more advanced material, which we will apply to a hero's fountain. We will construct this device and perform experiments. These videos are presented by Cecil, who is a retired engineer, with the help of his 2 grandsons. The goal is to make it simple enough so that all age groups and knowledge levels can get interested in it and participate. Before we start, this would be a good time to summarize what we already learned in Part 1. 1. Water pressure is the force or weight of water spread over a certain area. 2. Water flow takes place from high pressure to low pressure. 3. Pressure is typically measured with a pressure gauge and stated in psi or bar. Pressure is also related to the height of water or depth below surface. 4. Pressure is the same at a given depth, no matter what the surrounding amount of water is, whether it's a lake, a bathtub, or small bottle. 5. We showed how a typical siphon works and how it needs to be started for it to work. Okay. So having got that out of the way, we will move on to our main project. We mentioned very briefly about the project we were planning to do. We are going to show how to make an interesting device, which is known as a hero's fountain. Some people call it a heron's fountain. Not sure why. Hero was a mathematician and scientist who lived in Alexandria, Roman Egypt, about 2,000 years ago. He made many scientific devices such as this fountain, and also a steam turbine. Not sure whether these devices had any practical applications other than illustrating the principle of physics. If you look up on YouTube, there are many ways of making a hero's fountain. Some of these may be simpler than what we will show you. However, since we are going to perform some experiments, we will use this approach. Here we show a hero's fountain in schematic form. There are 2 sealed containers, in this case, plastic water bottles, which we call bottle number 1 and bottle number 2. On top of bottle number 1, we have a shallow tray to catch the water from the fountain. A tube 1A is inserted into bottle number 1 through the tray, and another tube 2A into bottle number 2. These tubes go all the way to the bottom. Water is pushed up through this tube 1A, which has nozzle at the top, to form the fountain. 2 short tubes, 1B and 2B, are also inserted into the bottles as shown. Now we have 2 flexible tubes, which we call connecting tube 1 and connecting tube 2. Connecting tube 1 is attached to the bottom of the tray and tube 2A. Connecting tube 2 is attached to tube 1B and tube 2B. It is important that both bottles and connecting tubes are all airtight. Hopefully, not too complicated to make. Right. As shown in the video, the tray has to be filled with some water in order for it to start. We have used green food coloring in the water for better visualization. If the fountain does not start right away, then unscrew the lid of bottle 2 about a quarter turn to release trapped air and quickly retighten as soon as flow starts. We have accelerated video to save time. But fountain flows for about 1 minute. Water level in tray stays steady. Water from bottle 1 keeps transferring to bottle 2. Again, the system has to be really airtight and no air bubbles for it to work. A description of the parts' use and their construction will be shown at the end of this video. To understand the principle on which this works, We will first take an empty bottle without a lid, stick a tube into it, and pour water down the tube using a funnel. The bottle will fill and overflow once full. Now, if we take same bottle and tube, but install an airtight lid and seal around tube, then water will fill a little bit and stop. When this happens, the air pressure created inside the bottle balances the pressure caused by the height of the column of water in the tube. This is illustrated in video. Remember, in part 1 we said pressure is related to height of water or depth below surface. Here we show how this concept is applied to the bottle with the airtight lid and the column of water in the tube. Hero's fountain works on this principle. In the previous slide 7 we showed how a column of water in a tube that is straight and vertical creates air pressure in a closed bottle. Now, this column of water does not have to be in a straight vertical tube. It can be in any curvy tube as well. As long as the difference in water levels are the same, the pressure in the trapped air is the same. Here we show how these principles are applied to our Hero's fountain. Air pressure in bottle 2 is created by water in tube 2A and connecting tube 1. Air under pressure is transferred to bottle 1 via connecting tube 2. Here it pushes the water in bottle 1 out of tube 1A to form fountain. Higher the difference in water levels, taller the fountain. Again, applying basic concepts of physics is the key to understanding many complex systems. What is the static height of the fountain? If we extend tube 1A high enough, then water will rise up in this tube to a certain height and stay there. There is no flow in the fountain. The height, hf, static, is the static height of the fountain, also called the head. This is displayed in the video, where we have placed the extension tube in a vertical position connected to tube 1A. Here again, some water has to be poured into the tray. In this case, there is no flow. But the water will rise in the extension tube as indicated by the small red marker, which moves up inside this tube. It will stop when the static height is reached and remain steady. If there are minor air leaks, it will fall slowly with time. Towards end of video, we show what happens when the two levels are the same. We have raised bottle 2 and removed the extension tube. As you can see, when the two levels are nearly equal, there is no flow, and the red marker stays close to the water level in the tray. This shows that the static height is close to 0 when levels are the same. For students who have basic knowledge in algebra, we show how to calculate the static height by setting up two simultaneous equations and solving for hf static. Note that the air pressure in each bottle is the same. Also note, we have used symbol pH to denote air pressure, which in this case is measured in inches of water. By solving the equations 1 and 2, we can show that the static height is equal to the difference in water levels in the two bottles, as shown in equation 3. Actual height can be calculated using data in next slide. So, what's so important about static height? Well, it is the pressure that makes the fountain flow. When the fountain is flowing, its height depends on the static height and size of the nozzle. Here we show how the measurements are taken. Printed scales are attached to the extension tube, bottle 1 and bottle 2 as shown. The static height, or head, as measured, is 11 inches plus 5 inches, which adds up to 16 inches. Level in bottle 1 is 8.5 inches, and level in bottle 2 is 3 inches. The height of the pedestal on which bottle 1 is placed is 11 inches. The measurements are tabulated as shown. Here we present the results of the static height test. Based on direct measurement of the static height, we measured 16 inches. However, by calculating indirectly using the height of water levels, we get 16.5 inches. The slight difference can be due to minor air leak and measurement inaccuracies. The maximum height of the actual fountain using the selected nozzle and 11-inch pedestal is about 10 inches. To increase the height of the fountain, we need to increase the difference in the water levels in the two bottles or reduce the size of the nozzle. This is the end of this video session. The goal of this video was to highlight some basic concepts of physics such as 1. Water pressure and the relationship with height of a column of water. 2. The interaction between water pressure and air pressure. 3. We applied these principles to a practical example in the form of a hero's fountain. Hope you now have a better understanding of the concepts of water pressure and its real-life applications. We will also cover other areas of science with practical examples and projects. If you like this video, please hit the thumbs up button, subscribe or send in your comments. Bye for now. In the next 2 slides we will provide more information about the parts, how they are made and put together. You may skip if you are not yet ready to make the parts. In the complete assembly, as shown, the bottle number 1 is placed on a plastic box about 11 inches in height. This can be any box that is strong enough to support the 1-gallon water bottle. A shorter height box may be used. The fountain height, in this case, would be lower. Also, we point out that, although we show the connecting tubes as one piece, we had to split them into 2 halves for ease of assembly, and join together in the final assembly, using the small tube couplers. Some Vaseline is applied to stop air leaks. Here we show the parts that go with bottle number 1. If you can get 1-gallon plastic bottles with 2-inch diameter caps, that would be very easy to work with. The tubes 1A and 2A should not touch the bottom. There should be a gap of about 1 inch. Again, the design as shown should be used only for guidance. You may modify parts according to whatever material is available. Here we show the underside of the tray assembly. All the tubes that go through the holes in the wooden strips should fit tightly using the all-purpose adhesive. The tray and cap are screwed on the wooden strip. The sealer has to be applied in between these parts and around the screws and tubes. The goal is to make it really airtight on assembly. Now we show the parts that go together with the bottle 2 assembly. Very similar to bottle 1 except there is no tray. Also, note that the wooden strip is shorter in this case. Here we show the features of the connecting tube assemblies. Again, they are both split in the middle for ease of assembly. The small tube couplers are used in the final assembly to join them. Note how the connecting tube 2 is looped on the top side of the tray, and connecting tube 1 is attached to the bottom of the tray. It is important to apply adhesive inside holes and sealer around the tubes. This is where we show the components used in the static height test. The extension piece, which is 18 inches long, is made with 1/4 inch inside diameter, rigid plastic tubing. The marker is made from the tip of a wooden chopstick, painted red. The scales were printed off from an online website. Now we see the stock tubing sizes that we used. The rigid plastic tubes had inside diameter of 1/4 inch and outside diameter of 3/8 of an inch. The same with the flexible plastic tubes. These were cut to size as needed. The nozzle was made from a toothpaste tube cap with a hole of 1/8 of an inch in diameter drilled through. In this picture we show the adhesives that were used. You do not have to use same, but anything similar would work. As an added precaution, some caulk may be applied around the joint between wooden strip and bottom of tray. Hopefully this information is helpful. Good luck with the project.